from chapter number 9. We will study complementary pass transistor logic CPL in this lecture. It's our dual rail type. CPL is a type of dual rail logic that we are studying for the last couple of lectures or so, and they are composed of NMOS transistors, and the whole concept of CPL is based on NMOS equations. And shortly we are going to see what are NMOS equations. Right. So for this given circuit, if we just concentrate on the left portion of, and we just neglect whatever is implemented on the in the right branch of the circuit. In the left branch of the circuit, we have this NMOS transistor, whose source is connected to B and gate is connected to A, and the output is drain. And what do we get on the drain? F. Of course, we get A dot B. This is the concept of pass transistor we have studied earlier in the course. A ANDed with B. If A is a 1, whether B is a 0, it is transmitted here. But if A is a 1 and B is a 1, we get an output voltage that is slightly lesser than B. We studied that in the course earlier, because NMOS is not strong logic 1 transmitter, right? But anyhow, neglecting that, we get A dot B if A is a 1. So we get an AND function. We get an AND function here. But what happens if we have A is equal to a 0? This means this NMOS transistor is not on. So what do we get at the output then? If this is the only NMOS transistor and this right branch is not present, what do we get at the output? We'll get a high Z output. High Z output means that nothing is implemented. We have the not connected output is not connected to input. In order to cater for those input combinations for which A is a 0, we introduce this right branch. And this right branch has a gate voltage or a gate logic that is complement of the logic that we implemented here, the complement of A. This ensures that when the input is logic 0, this is when A is 0, this is a 1, logic 1, and this is logic 0. So for the input combination, for the two input combinations for which A is equal to 0, these two combinations of the truth table, when A is equal to 0, this transistor is off, and this transistor, the right transistor, is on, and we get A, that is a 0, at the output. So when A is a 0 and B is a 0, we get a 0 at the output. And when we have A is equal to 0 and B is a 1, whether B is a 1 or 0, if this A is a 0, this transistor is off and this transistor is on. So we get a 0 here. And for the input combination 1, 0, this means this transistor is now on. This left transistor is now on. When A is a 1, this transistor is on, and this transistor is off. Because now we have A is equal to a 1. This means A bar is equal to a 0. So this transistor is off, whereas the left transistor is on. And whatever is on B will get at the output. So here we have B is equal to 0, we get a 0 at the output, and now we have 1, so we get a 1 output. So this two table tells us that it's a 2 input and gate, and it has verified all the entries that we have in a truth table of AND 2 input AND. So this is how we can implement an AND operation using pass transistors. So why is the right branch here? I have already explained why is the right branch, because if the right branch is not there, we'll not be able to verify the complete truth table. So in order to verify all the entries of a truth table, we have to have this right branch, right? So it's A dot B plus A complement A complement A is a 0. So A dot B or 0 is A dot B, which is an AND operation. Right. So making a two output version, since it's a dual rail logic technique, so CPL of a NAND will also have an AND, or CPL of an AND will also have a NAND as the other output. So this is a CPL NAND AND pair. Right, let's take it in the picture, the whole circuit. Now it is. Right, so we have B, B plus A bar A. So AB plus A bar A is A bar A is a 0. So we get AB. This means we have this AND operation implemented here. So this implements, F implements AND operation. What's about this right portion of this circuit? I hope it should implement a NAND. Right, so we have this A connected to B. It's not B, it's not just B, it's B bar. A connected to B bar, so this is A B bar plus A bar ended with A bar. A bar ended with A bar is A bar plus A B bar. So applying distributive property is A bar plus A times dot ended A bar plus B bar. So A bar plus A is a 1 ended with A bar plus B bar gives us A bar plus B bar. So applying De Morgan's law gives us AB complemented, which is NAND 2. So with this simple arrangement, we get a CPL implementation of NAND oblique AND. Right. We can go along with the same concept and can implement a CPL NOR OR pair. A CPL NOR OR pair works like this: is A bar ended with B bar, or A ended with A bar. So A ended with A bar is a 1. So this gives us A bar, B bar, or A plus B, the whole complemented, which is NOR 2. And the right side, the right portion of the circuit it should implement an OR. So A bar B plus A. Right, so this gives us A bar B, this A bar, this B, this A, and this A. So A bar B or A gives us A, and applying the distributive property gives us A plus B, which is OR 2. So this is how we can implement a CPL NOR OR pair. And before we finish today's lecture, let's see how can we use CPL implementation, complementary pass transistor logic implementation for exclusive OR, exclusive NOR pair. This is very simple. We know that A exclusive OR B is A complemented B or A B complemented. So A complemented B, A B complemented. So it gives us exclusive OR 2, and A complemented ended with B complemented, or A complemented A ended with B. And we know that gives this is actually the complement of this, right? Exclusive OR 2. So it's exclusive OR 2, it's exclusive OR 2. So that's all for today's lecture. And in the upcoming lecture, we'll hopefully be studying CPL, more examples from CPL. Thank you.